So here is the p-value method. These are general instructions to interpreting a p-value. P-value, first and foremost, is a probability. It is between 0 and 1. Sometimes it could equal 0, sometimes it could equal 1, but it's usually between 0 and 1. Formally, p-value is the probability of rejecting the norm merely by chance. So without any effect at all, what are the chances that you are rejecting the norm merely by chance? Informally though, you can interpret the probability of error if the norm is rejected as p-value. The other informal interpretations are the amount of probabilistic support offered by the data toward the norm is the p-value itself. The amount of probabilistic support offered by the data toward the alternative is 1 minus p-value. P-value is dependent on the type of test. So for a two-tailed test, the p-value is 2 times the area above the absolute value of test statistic. For a right-tailed test, p-value is the area above the test statistic. And for a left-tailed test, the p-value is the area below the test statistic. Now, how do we find this area? This area, note, the area is the area under the curve. The density curve, and it's obtained using CDFs. CDF stands for cumulative distribution function. How do we obtain a conclusion using the p-value method? We always ask this question: is p-value less than or equal to alpha? If you say yes, you reject the norm. If you say no, you fail to reject the norm. This is always true. Take an example. Suppose alpha is decided to be 0.05 and we get a p-value of 0.7621. So I'm going to ask myself this question: is p-value less than or equal to alpha? If I say yes, I will reject no. If I say no, I would fail to reject no. Clearly, in this problem, alpha is 0.05, p-value is 0.7621. Is 0.7621 less than or equal to 0.05? The answer is no. So I fail to reject no. How would I interpret this? Well, if hypothetically, if no is rejected, the probability of error in conclusion, or in such conclusion of rejecting the no, is 76.21%, which is equal to the p-value. Would you like to make a conclusion where you make 76.21% error? In other words, would you like to make a conclusion where you know that you would be wrong, the probability that you are wrong is 76.21%? Nobody would want to make such a conclusion, a wrongful conclusion, so I shouldn't be rejecting the norm. So I failed to reject the norm. Take another example. Suppose alpha is 0.01 and p-value is 0.0072. You ask yourself this question: is p-value less than or equal to alpha? If you say yes, you reject null, and if you say no, you fail to reject null. Well, clearly in this problem, alpha is 0.01, p-value is 0.0072. Is it less than 0.01? The answer is yes, so I say reject null. So how would I interpret it? One interpretation is, if null is rejected, which is the case in this problem, the probability of error in such a conclusion, which is null is rejected, is 0.0072 or 0.72%. So if I concluded that I should reject the null, what is the chances that my conclusion is a wrongful conclusion? It's only about 0.72%, which means it's very small error. So the data is giving me a clear indication that I should be rejecting the null. So in this particular problem, we reject the null. You may always wonder, why do I need this alpha? Now, we're comparing it to alpha because this is the permissible amount of error that the researcher allows. So I say any error less than 1% is acceptable, and if I get 1% or below error, then I will reject the null. And that is the case in this problem. 0.0072 is less than or equal to 0.01, so I can happily reject the null and be content with this particular conclusion. A more informal way of seeing this is by finding probabilistic support or evidence toward the alternative and null. So the evidence toward the alternative is 1 minus p-value, and the evidence toward the null is the p-value itself. So 1 minus 0.0072 is 0.992a. So if you use this informal interpretation, you'd see that, well, the amount of probabilistic support toward the null is close to 0%. The amount of support toward the alternative is close to 99%. So if I've repeated this test 100 times, 99% of the time I'm going to agree with the alternative, 1% of the time I'm going to agree with the null, which tells me that the alternative is more likely to be true than the null. Although this is a informal approach that is usable, this approach can get confusing unless you are extremely comfortable with p-values. Therefore, I recommend that you use the approach which is over here, which is, if the null is rejected, the probability of error in such a conclusion is 0.0072 percent. I mean 0.0072 or 0.72%. So what I'm trying to say is the formal interpretation is great, but if you want to use the informal interpretation of the p-value, I would recommend the first one would be the easiest. You can use the later two explanations, informal explanations or interpretations, but it might get quite confusing in certain situations. But if you can follow the formal interpretation, more power to you. It is great. But if you're having difficulties understanding the formal interpretation, you can use the first informal interpretation to get better sense of p-values. So keep in mind, This is a very generic procedure or generic video about how to interpret p-values and how to use them in finding a conclusion for a statistical test. Because in a practical situation, you have to find the p-value from a software or using the distribution, CDF, and so forth. That is the p-value, and I hope you know more about p-value now than what you knew 10 minutes ago. Thank you for watching this video.